Okay, so this is the lecture 3, I guess, of topological vector spaces. And in the uh, previous lecture, we had discussed a very important result, which said that we can recall. We had said that um, we can locate all informations. We can locate all informations about the topology of a topological vector space with having knowledge only about the local properties of the local properties, right? And how were we able to do this? If you recall, that in the previous lecture we had set up two functions, which were the translation by a vector and which was scaling by a vector, and we had proved that both are homeomorphisms of a topological vector space onto itself. Once we restrict that they are homeomorphisms, so they will obviously relate the properties related to topology from the domain to the codomain, right? Homeomorphism is the other way of saying it, they are topologically the same, right? But the translation actually works in a way that, since the translation is a homeomorphism, so if you recall, we had defined the translation by a vector a from x to x by just any element getting mapped to a plus x, and we had checked that this is a homeomorphism, right? And the checking of homeomorphism was also quite trivial, because you can easily see that you can actually construct out see, this can be easily seen to be injective from the vectors properties of the space, and in fact you can easily check it to be an inverse can be easily constructed by using the additive identity of the vector which we are using to translate it, right? And you can actually just talk of it in that way. Surjectivity can also be shown very easily. So we had covered these things in the last lecture. Yeah, so what conclusion did we draw out from here is that this means that if I have some subset of x is this topological vector space which is open, then I can scale it by some vector, and this will also be open, because this is a homeomorphism. The scaling is a homeomorphism, right? Okay, and this phenomenon was something which we called that it to be, or rather, this is an if and only if statement. That is, if this is open if and only if a plus e is open, and I can check this for all vectors a coming from x, and this was a property which we call translational invariance. So it's translational invariance. And then we had a series of definitions which came as a list. So I'm just giving up a quick review to those. So these were the definitions where we covered the concept of being, okay, so let me just yeah, okay, so something being locally convex, something being locally bounded, something being locally compact. You can obviously see that all the properties which we are discussing or which we are defining in order to discuss later are some local properties, local topological properties, and everything is some sort of related to the local base, which is a collection of neighborhoods of the origin. Okay, when is x metrizable, that is when can I find a metric compatible to the topology already endowed on it. Then what is an F space, what is a Frechet space? Frechet was the godfather of metric spaces. When is a space said to be normable, that is when can I find a norm which is compatible with a metric, and the metric is compatible with the already endowed topology. And when is X is said to have the Hein-Borel property or the HBP. Right. Now there are certain relations between these properties which we will not prove immediately, but we will come to them later. So I can just come up with those properties listed. So yeah, what is happening? Okay, right. Okay, so some properties. Okay, this we'll see later. The proofs of this will come eventually. But before that, we need to study separability, which we'll do a bit later, I guess. So number one is that so we are assuming that we have a topological vector space X. Okay, so X is locally bounded. So what was the definition of something being locally bounded? If you recall, then it means that there is a neighborhood, there is a bounded neighborhood of the origin. Okay, there is a bounded neighborhood of the origin. In that case, we say that X is locally bounded. So X is locally bounded implies that X has a countable local base. So this is one important property. The next important property is that if X is metrizable, that is, I can find a metric on X which is compatible with the already defined topology on X, then X has a countable local base as well. As a countable local base. Then we will see that X is normable. That is, I can find a compatible norm on it. X is normable if and only if X is locally bounded and locally convex. Right? So what was the definition of locally convex again? So it means that there exists a local base of the origin which is convex, whose members are convex typically. Okay. The next property which will be important is that a space is finite dimensional. Now we know what a finite dimensional space is. I'm not going to elaborate that, but okay, still for completeness. So in a very geometric sense, I would say that a space is said to be finite dimensional if I can get mutually orthogonal vectors which determine all possible directions available on the geometry of that space. Or if I go in some sort of the algebraic notion of it, so finite dimensional means I'll get a finite linearly independent set which will span the entire space. Okay, whose whose linear combinations taken with the coefficients coming from the underlying field will give all the elements of X. Okay, so X is finite dimensional if and only if X is locally compact. X is locally compact. So again, recall what it means to be locally compact. That a space is said to be locally compact if the origin has a neighborhood whose closure is compact. Okay, fine. And the last important point is that if a locally bounded space X has the Hein-Borel property, then X is finite dimensional. So these are the 5 important properties of topological vector spaces which we will be proving eventually as time goes. And yeah, so these properties are something of very important to have complete knowledge about the topological as well as the vector space properties of a space given, because you can see that if I know it's locally bounded, I can talk something about the bounded topology on it, or something about the topology being bounded in some sense, because I can what I said, I can always just just translate out the local properties in terms of open sets to global properties, right? And the finite dimensional it is coming out to be some sort of, what do I say, the vector space property. So it also, it's related to the topological properties, and not only the topological properties but locally topological properties. So in some sense, those homeomorphisms are somewhat helping us to gain knowledge about only the local properties and tell everything about the uh, endowed structures on the space, be it the vector space structure or be it the topological structure. Now there are some important examples which uh, you know claims the falseness of a converse to this theorem, but those examples are some certainly non-trivial, so I'll exclude those at this point. But later I might think of them, discussing about them in some sense. But rather, when we'll discuss or come up to the proof of some of these statements, I'll try to explain whether the converse holds or the converse does not hold, in terms of counter examples, or simply in terms of the idea why it should or why it should not hold. Okay. Okay. Fine. Now let us quickly discuss the notion of separability. We'll do it uh, in a very rigorous sense, but we'll see that it has some very important consequences. So, separability. So, as the name suggests, I think guys, those who have taken topological spaces or studied topology, they also have a notion of separability, where we have, I guess, 4 to 5 notions of separability: the T1 space, T2 space, T3 space, and so on and so forth. But it's actually related to that only, and it's somewhat a more fundamental sort of a statement. Okay, let's get into it. Theorem that suppose K and C are subsets of a topological vector space X. Okay, given, so what are we given? Given K is compact, C is closed. Given K is compact, C is closed, and both of them are disjoint, K intersection C is empty, then the origin has a neighborhood V such that, so the origin has a neighborhood V such that K plus V intersection C plus V is empty as well. Okay, so this is the basic statement of the separability, that if I choose two subsets of a topological vector space, one is compact, one is closed, and they are disjoint, then I'll get a neighborhood of V, a neighborhood of origin, which is V, such that if I translate V by the vectors in the compact set, and if I translate V by the vectors in the closed set, it's still disjoint. Okay, so to prove this will require a separate notion, but some things which we can immediately observe. So rather I can state them as properties, that we can observe that this K plus V, this can be actually treated as the union of the elements X plus V such that X comes from K. Right? Now recall what we had studied by the homeomorphism of the translation action, or sorry, the translation operation, that that for all vectors X in capital X, X plus V is open if and only if, right, X plus V is open if and only if V is open, right? This we had studied. So now we are given V to be a neighborhood, so V is open. That means X plus V is open for every X in X, therefore for every X in K. And we also know from the basic definitions of open sets, or basic definition of topology, that arbitrary union of open sets is still open. So this implies that K plus V is an open set. So K plus V can be readily understood to be open sets. And it's not just open set, but it's an open set containing K, which we can immediately observe. Okay, clear? Similarly, we can also see that C plus V, this will also be an open set in the same argument. This will also be an open set containing C. So what we actually have here is that we actually have here two open sets, two disjoint open sets, one containing the compact set K and one containing the closed set C. So the main idea of this theorem is basically that we get hold of disjoint open sets, one containing K, which is a compact set, and one containing C, which is a closed set. Okay, so in some sense we are able to separate a compact set from a closed set. Both are initially disjoint, so we are able to separate a compact set disjoint from a closed set topologically. Topologically means in terms of open sets. Okay, fine. So the proof of this theorem, so if I talk about the proof of this theorem, the proof requires a lemma. Let me just state it here. Okay, let me just state it with this color. A lemma. Okay, so what does the lemma say? The lemma says that if W is a neighborhood of the origin in X, X is still a topological vector space, then there exists a neighborhood U of the origin which is symmetric, What do we mean by symmetry? That U is same as minus U. Minus U means multiplying each of the elements by minus. Minus means the additive inverse. Okay, so which is symmetric and satisfies that U plus U is contained in W. Okay, fine. So how do I prove this? The proof of this lemma. Okay, the thing which we can immediately sort of how do I say this? See, we know that the origin added to the origin is still the origin, right? A very lame statement, but what we know is that this operation is continuous, right? This operation is continuous. So recall from the definition of continuity, this implies that so now W is given to be a neighborhood of the origin. So this implies there exists neighborhoods V1 and V2 of the origin such that V1 plus V2 is contained in W, right? Okay, now I'll just choose U. So I'll just choose U to be V1 intersection V2 intersection minus V1 intersection minus V2. Now these two are still open because recall again that we had also shown that scaling is a homeomorphism. So we are just scaling here by minus 1. So there's no problem in it. I have a finite intersection of open sets, so it's open, and each of these sets will contain origin because V1 and V2 are neighborhoods of the origin itself. So U will satisfy the required properties. You can check that, that's a routine exercise. So choose U, then U is the required neighborhood. Okay, and moreover I can actually keep on continuing this, right? Because so this is just a remark that this can be continued. How do I continue this? How can I continue this? So I can just replace W by U, and then I can show that there exists some neighborhood which will eventually satisfy the same property, that U plus U is contained in U. But then if this happens, then that means U plus U plus U plus U is contained in W, and I can keep on going like that, right? So the only thing we require here is that U needs to be symmetric. That is to be kept in mind. Okay, so now let us come to the proof of the theorem. So yeah, let me add an extra page. Okay, so proof of the theorem. proof of the separability, separation theorem. Proof of the separation theorem. Okay, wait a minute. Let me drink some water. Okay, fine. Now, if the obvious trivial case would be if K is empty set, right? Because if K is empty set, then K plus V is an empty set. So there's nothing to prove. So we'll start our proof with K being non-empty. So let K be non-empty and consider a point X coming from K. Okay. Now since C is closed, C is closed and X is not in C because we had chosen K and C to be disjoint. So what can I say from here? So I have K is not empty. I choose a point X from K. I have C is closed and X is not in C. Okay. Right, but from here I can say okay, I think I'm getting it. Right. So and also recall, so this for completeness, that translation or rather the topology on X is translationally invariant. Is translationally invariant. Fine. Then by our previous proposition, 0 has a symmetric neighborhood. 0 has a symmetric neighborhood. So let me just go back to the statement of the theorem once. So I am having a neighborhood V of the origin. So I need to use the lemma because the lemma also deals with the neighborhood of the origin, and obviously we gave that lemma for the proof because we need it at some point. So in my previous proposition, or rather I should say the previous lemma, or I just forgot whether I wrote it as a proposition or a lemma, but so I'm just linking towards the exact previous statement which we stated. So in my previous lemma, 0 has a symmetric neighborhood Vx such that X plus Vx, it still holds the openness, plus Vx intersection with C is non-empty, as this part will be in K. You can actually observe it clearly, and by the symmetry of Vx, since Vx is exactly equal to the collection of all its additive inverses in terms of the group structure, X plus Vx, this will be its intersection with C plus Vx will be non-empty as well. Okay, will be non-empty as well. Right. Now since I have K to be compact, so I'll get only a finite number of open sets which cover K. So there exists finitely many points x1 till xn in K such that K contained in x1 plus vx1. So this is one of the open sets, then I can continue this till xn plus vxn. So this will serve me, or rather sorry, I need to, yeah, so this will give me an open cover for K. Fine, but then put V to be Vx1 intersection Vx2, and I can continue this till Vxn. What then? Then what is K plus V? So K plus V is, or rather it should be contained in the union of I is equals to 1 to n xi plus vxi plus v of all these unions. By the way, K is constructed, and by the way V is constructed, but then this is contained in the union of xi plus vxi plus vxi, I is equals to 1 to n, and we know that this is disjoint from C plus vxi, right? right? This is disjoint from C plus Vxi, so this turns out that the proof is complete. Fine. Okay, got it. Now there's a very special case to it. I'm just adding up this, that now C plus V is open, right? By definition, C plus V is open, and K plus V does not intersect C plus V, so the closure of it also won't intersect C plus V. But not intersecting C plus V is stating that it won't intersect C either. But then if I take K to be 0, okay, so what I have is that the closure of a neighborhood of V does not intersect C, right? Right. So how can we state it? So this gives me the theorem that if B, because we are working over neighborhoods of the origin, right? V comes out to be neighborhood of the origin. So if B is a local base for a topological vector space X, then every member of B contains the closure of some member of B. Okay, try to justify this out. Okay, it has something to do with it not intersecting and this closed set. Okay, just try it out. I won't think it will be difficult for you at all. The next important consequence of it is being Hausdorff, and that's actually pretty trivial. Okay, at every, so since we have proved the separation for every for an arbitrary vector space, every topological vector space X is Hausdorff. And how is it so? We know that singleton sets are closed in a topological vector space. It was the axiom or the definition of a topological vector space. So simply choose K and C to be, choose K and C to be distinct points as sets, points as sets. Now you can easily observe that it's a very trivial observation that every singleton set is compact, right? There's nothing there actually. And singleton sets are closed by the definition of topological vector space. So just choose K and C to be distinct points as sets and apply the separation theorem. Apply the separation theorem. And we know that being Hausdorff is essentially required from the point of view of sequences, but in itself Hausdorffness is a very important property for topological spaces. And we have also, so we just now see that every topological vector space is Hausdorff as well. Okay, yeah, so let this lecture be up till this much. In the next lecture we will be coming up with some more properties of the separations, and we'll discuss some more important things. So meet you guys in the next lecture.